Hello everyone, so let's look at how we can calculate the ionization constant of some acids and bases using the pH and the initial concentration of an acid or a base. So specifically in this example, we're given methylamine is a weak base, and we're told that if the pH of a 0.065 molar solution of this amine has a pH of 11.70, we need to determine Kb for this amine. And I've gone ahead and I've written down the equilibrium for this amine in water. So we're told it's a weak base, so that means it will act as a base, a Bronsted-Lowry base with water. Water will act as the acid, and the water will protonate it, leading to an equilibrium where there's a protonated conjugate acid of the amine, and then of course hydroxide will form. And that's of course why this then has a quite a high pH, so meaning a pH larger than 7, which is 11.7, because of the formation of the hydroxide ions. So it all kind of makes sense. That's why it's a base. And we will now need to determine the Kb. So let's write down the Kb for this equilibrium. So determining, so the products are of course CH3, NH3 plus at equilibrium, OH minus at equilibrium, and the CH3NH2 concentration at equilibrium. Right, water doesn't form part of the ionization constant expression because water is a pure substance, it's a liquid, so it has a value of 1. Right, so we need to determine what those concentrations are at equilibrium, and hence we will be able to determine the ionization constant, the equilibrium constant. And the way that we determine equilibrium constant is by using an ice table. Right, so let's go ahead and draw our ice table. So I've done that in advance just to save some time on the video. So of course you can do that on your own time. So this is what you have, right? You take your equation and we take our initial information. So our initial information is that we take the solution concentration of the amine as the initial concentration of the amine. So that's 0.065 molar. Remember, we work in molar. The water doesn't form part of the ionization constant expression, so hence it's not applicable in this case. And we're looking at the initial conditions. So we're modeling this as if we took the amine and initially dissolved only that in the solution. So hence we put a 0 for both of the species that the base dissociates into. All right, now the question is the change. What do we determine the change as, right? So the change is always x in all cases. And we need to determine whether or not the reactants decrease or increase, or the products increase or decrease. And what we always did is we calculated the reaction quotient, and you can quickly hopefully see by now that the reaction quotient in this case is 0, right? So Q is equal to 0 because it's going to be 0, 0 divided by 0.065, which is 0. So when the reaction quotient is 0, so you see, because we model acids and bases in this manner, Q is always going to be 0, and hence why we always have a decrease in the acid concentration and an increase in the product concentrations, right? The ions that it dissociates into, right? Because the forward reaction is always favored to proceed towards equilibrium. All right, so that makes sense. I mean, so that's what we get to. So then hence at equilibrium, we have the 0.065 minus x. Of course, there's no change applicable for the water. at equilibrium, the water's concentration, it's not applicable because technically all those values are just one. We don't put it in the ionization constant expression, so we just ignore it. And we have our equilibrium concentrations for our dissociation species, our ions, are X. So that means to calculate Kb, we can write it out. And if we plug in these expressions that we have, it means that it will be X multiplied with X divided by 0.065 minus X. And we can simplify this to X squared divided by 0.065 minus X. Right, we want to calculate the value of Kb, so we need to find a way to determine the value of X. And the other thing that we're told is that the pH of the solution is 11.70. Right, so what does the pH of a solution tell us? 11.70. Well, if you recall that the pH plus the pOH of a solution is equal to 14.00. So, for this solution, the pOH is equal to 14.00 minus 11.70, and so the pOH is equal to 2.30. And from the pOH, we can then determine the concentration of the hydroxide ion, right, at equilibrium, because that's what the pH tells us. It always tells us what is the concentration of hydronium or of the hydroxide ion at equilibrium. Right, so we can make use of this. So that means the hydroxide ion concentration is equal to 10 to the power minus the pOH. And maybe I just need a bit more space here. I'm just going to move that to there. So this is equal to X, right, because it's the hydroxide ion concentration at equilibrium. And this is equal to 5.011, keep all the numbers, times 10 to the negative 3 molar. All right, but we can plug that now into X. So that means we can calculate Kb, because it's going to be equal to 5.011 times 10 to the negative 3 squared divided by 0.065 minus 5.011 times 10 to the negative 3. And then we can round this answer so to two significant figures, and I got 4.2 times 10 to the negative 4 for Kb. All right. So that is the important thing, is remember, so you can always use the pH or the pOH to determine the hydroxide or the hydronium ion concentration, and that is equal to the hydroxide or hydronium ion concentration at equilibrium. So for the acids or bases, that's important. So that always gives you your this value here, so the concentration at equilibrium. So that's an important factor. So if you need to calculate the pH, of course, you work the other way around. Then once you got X, then you can calculate the pH or whatever. But if you're given the pH, then you can work the other way around. Okay. So, yeah, that was this problem. So the answer is Kb is equal to 4.2 times 10 to the negative 4. It's not a small Kb, it's small-ish. I mean, it's not large by any stretch of the imagination, but it's not that small. It's not as small as 10 to the minus 10, for example. So meaning this equilibrium is slightly reactant favored, but it's approximately 1. So it's neither reactant nor product favored, really. We can't really say. We can and probably slightly reactant favor. That's what I would say. Yeah, but okay, cool. The idea was actually just to calculate KB and go through the mechanics of this problem. Right, thank you for watching, and I'll see you in the next video.